The broadcast is now starting. All attendees are in listen-only mode.
Welcome to our Emerging Issues webinar. Today's topic is a space weather catastrophe on the horizon. And we are only a couple of days away from autumn, and I hope everyone is getting in settled and ready and has their pumpkin spice lattes because we're about to launch here. I'm your host, Andy Blanchard, and I lead our Emerging Issues team at Verisk. And if you couldn't tell from my mention of launch, we are going to be focusing on space today, and specifically space weather, with a little bonus topic at the end, but we'll get to that later. But before we jump in, as usual, I am going to begin with our policy statement. The policy of Verisk Analytics and subsidiary companies is to comply in all respects with federal and state antitrust laws. With this in mind, we want to mention that during all seminars held under our auspices, this policy prohibits discussion of certain topics. Because we want to avoid even the appearance of an antitrust violation, we go beyond the letter of the law, and we will not discuss any matter that violates the spirit of the antitrust laws or could be perceived as doing so. A copy of our policy statement on discussion at meetings can be found at verisk.com/statement. And to keep us on track today, we're happy to have Verisk attorney Jason Kurtz along for the ride. Thank you, Jason. We appreciate your guidance and help in preparing for today's meeting. And before I introduce our experts, just a couple of quick notes. I've gone through these things before, but I want to make sure everybody knows. We want to hear from you. There is a chat function in GoToWebinar, so use that, share your reactions, throw questions at us, anything that comes to mind. Only we here at Verisk can see what you put in the chat. Sometimes we get more questions than we can answer during the event, but no worry, we always endeavor to nonetheless get back to folks afterwards if we can't get back to you live during today's event. And last, we will be sharing these slides, so just keep an eye out for the material in an upcoming circular, and I say that so folks can really pay attention and listen and see what's before them and not have to feel like they have to take copious notes. You'll first hear from Cordula Robinson, Division Vice President, and Mark Leidner, Division Sector Lead from our Atmospheric and Environmental Research Division. And then Eric Gage, Product Development Analyst from our Commercial Property team, will share her insights. Cordula, please take it away.
Thank you. Hey, it's really great to be here today. And my name is Cordula Robinson, and I am the VP of Space Weather in the Lexington office. I have been in space science and space AI for quite a few years now, originally getting my PhD in physics and astronomy from UCL, and then going on to do a postdoctoral at what was then the Harvard-Smithsonian Center for Astrophysics, and that is what brought me to the US, and I've been here ever since. And my section lead and chief scientist is Mark Leidner, and he may want to say a few words too.
Hi, good morning, everybody. Indeed, I'm a long timer with AER, Atmospheric and Environmental Research, at 27 years as a staff scientist, and now as an engineering section lead over the Space Weather Division. And we're just excited to bring what we know of space weather risks and the science to this webinar today.
Next slide. All right, so why space weather? Well, it is all driven by the sun, and the sun is a very fiery place, and we can start the video and it will show you some of the magnetic effects or field effects of the sun, which is not at all like what we're used to on Earth. On Earth, we've got a really uncomplicated magnetic field. We've got a North Pole and we've got a South Pole, but it's not like that on the sun. On the sun, it's really highly chaotic. And it's generated by this magnetized fluid. And a lot of the energy that the sun has is because of all the hydrogen that resides there, and the energy is all fueled by fusion, and you get 4 hydrogen molecules creating 1 helium model, and just this massive amount of energy and all this magnetic fields associated with it that really twists like this, like like almost like elasticized rubber bands, and when it knits, when it becomes so tight, it reaches the elastic limit and just like flares out. And it's during these moments of it flaring out and releasing energy that we experience large amounts of space weather. So as I say on the slide, the charged fluid moves around with huge temperature gradients, and these gradients will last for at least another 5 billion years. This is not on a small order of time. There's a lot going on in our sun. And the magnetic field can be dragged around and really violently reconfigure. And that's what creates the explosions and the space weather that we're a little bit subjected to on Earth. Our satellites certainly are, and the International Space Station is too. And space weather can be mild. So we can go to the next slide. Yeah, so space weather can be as mild as auroras or as severe as coronal mass ejections that lead to power outages. So here we see that every 11 years, the sun's magnetic cycle snaps. That's like when I was referencing like the elastic band reaches its elastic limit. It just snaps, and the sun's own main magnetic pole flips, although there are all these interstitial magnetic fields as well. And when it snaps, we call it the solar maximum, and we are due for another solar maximum in 2 years. So a lot's about to start happening, and maybe if you follow the news, you may be hearing that, oh, there's lots of auroras in the sky, or there may have been an incident and that went in the direction away from Earth, but had it had come to the Earth, it would have created internet outages. So things are going on, and it's really just fitting the natural cycle of the sun. And during the solar maximum, you can get just more sunspots, more energy, more solar eruptions. And I think if we move on, there's like, it's not going to be the next slide, but there's next points. Yeah, exactly. So the next solar maximum is due late next year to mid-2025. And we may expect during this time that we're going to have more impacts on radio communication, potentially power, and we'll all be on the lookout for that. Similarly with radio navigation, which really impacts our global positioning signals. And that's all what ties into the satellites that surround the Earth and provide very precise timing and navigation. So all of our Google Maps, all of our farmers' activity in the Midwest, all of our Wall Street activity with timing. So it's very essential that we're very vigilant and know what's happening with space weather and how it may create impacts. And so too with satellite communication. So we can go to the next slide. So usually on Earth, we're not so fussed about space weather directly hitting us on the surface of the Earth, because we have this protective shield around it that is called our own magnetosphere. And it's got this like angelic kind of shape to it, which is what you see in the image on the right. So we're protected from a lot of this space weather by this magnetosphere. And it's played, the magnetosphere itself has played a crucial role in us being able to live on planet Earth, our planet's habitability. But what you do see in this diagram on the right is that the magnetosphere is weakest at both of our poles. It kind of reaches the surface of the Earth at the poles. So there we have to be very vigilant about space weather effects. And there's been some assertion that potentially when you fly over the poles region, you know, this may be leading to higher cancer rate for flight crews and so on and so forth. And if we go to Antarctica and do expeditions there, sometimes our outfits are very protective anyway, just from the cold, but maybe also potentially from space weather. So if you're dressed like an astronaut, you're probably going to be resistant to the space weather effects. But because it's weakest at the poles, this is important, and we'll talk to that soon. So next slide. So some typical space weather phenomena, some you may be very familiar with, are aurora, which are beautiful, coronal holes, coronal mass ejections. So aurora, we usually see those at higher latitude, and we usually see those at certain times of the year. And people may go to Iceland at the end of August and September specifically to see the aurora. I grew up in the north of England. I saw aurora every now and again because we were 55 degrees north there. And they're very, very beautiful. We may call them the northern lights or the southern lights, and they really happen when you get in solar electrons colliding in the upper reaches of the atmosphere. And it's our magnetic pole, our dipole pole, that energizes these electrons and sends them in more polar regions, which is why auroras are constrained there. Coronal holes, they are also space weather phenomena that we don't experience as directly on Earth, but they equate to dark regions on the surface of the sun, and they're dark because they're cooler. And this means you get high-speed solar wind escaping from the surface of the Earth right into space. And these high-speed winds may interact with the more ambient and slower winds and create these like co-rotating regions that also then interact with the Earth and cause geomagnetic storms. And that they may buffet the Earth for many days, and they can disrupt navigation and power grids, and we really do try and forecast them, which is what we'll speak to soon. They may even have some effects on nervous and cardiovascular systems. So some people say, oh, it's the full moon, I'm feeling really anxious. Well, maybe if you're nervous, it's because there's a geomagnetic storm coming. So be aware of that in the next next 2 years. I mean, this is all nature's force. And then we have coronal mass ejections, and these may be the most well-known, and these are very large expulsions of plasma and again magnetic field from the sun's corona. They travel outward very fast at around 250 kilometers per second. And sometimes they reach our planet in 15 to 18 hours and may be accompanied by solar flare. And this is actually, we can go on to the next slide, I think, if I'm, oh no. Well, the coronal mass ejections, the most famous one is the Carrington effect that happened in 1859. And led to this 9-hour power outage. But just to talk to solar flares, I'm going to hand over to Mark, and yeah, we can talk about forecasting a bit. It's all yours, Mark.
Okay, thanks. Yeah, you may start the video. So this is a video of a solar flare as it occurred April 17, 2016, and you can see this very large bright flash occurring on a certain portion of the sun. That is a release of energy and matter from the sun. You can see it sort of evacuating straight away from the sun there. These, as Cordula described earlier, the energy stored up in those magnetic field lines as they become more and more twisted and contorted can eventually break. And this allows for an ejection of matter from the sun directly out into space, and also direct emission of energy in the X-ray range, which is much, much shorter than even visible light. It's very high energy. Now, because this happens at different parts of the sun at different times, the sun is rotating, the Earth is rotating around the sun. Not all of these events affect the Earth. But if we happen to be in the crosshairs, these events can take from a few hours to a few days to reach us. So if you can move on to the next slide, please. So as Cordula mentioned, the most famous coronal mass ejection was this so-called Carrington event in 1859, and it still stands as a benchmark event for affecting Earth's electrical and communication systems. So the stronger the event coming out of the sun, and the more directly connected to the Earth, the faster it gets to us. So again, I mentioned it can be from hours to 2 or 3 days. So there isn't always a lot of time to predict. It's noted here that in 1989 there was a hydroelectric transmission system that was temporarily knocked out from another large solar coronal mass ejection. So this leads us to ask, how predictable is this? This is a natural phenomenon, the world happening around us and the space environment affecting Earth. How predictable is this kind of event? So if we can go to the next slide, please. So let's talk a little bit about space weather forecasting. I spent the bulk of my career working on terrestrial weather, that is, the day-to-day thunderstorms and weather systems and high pressure systems, the things that we all experience. Space weather does not resemble terrestrial weather in very many respects. So I kind of want to bridge the gap between what we understand and know about terrestrial weather to space weather. So in terrestrial weather, we think about the variation day to night, the daily diurnal heating and cooling cycle. We think about seasonal changes from summer to winter, year to year variability. We think about El Nino, La Nina. There are all these effects that contribute to variation in terrestrial weather. Well, space weather also has quite significant day to night differences because either the sun has an input on the bright side of the Earth or it's shaded on the dark side. That's similar. But the forcing from the sun is far more chaotic than our terrestrial weather, and the events can be much larger in magnitude and happen much more rapidly than in terrestrial weather. There is one very long solar cycle that Cordula alluded to earlier, being the 11-year solar cycle. But the solar mass ejections, these coronal mass ejections, can come up suddenly. And if they happen to be on a part of the sun that's connected to the Earth at that time, we will feel the impacts again in hours to days. So in terms of forecasting, there is a way that the sun's influences move outward from the sun into the solar system. So both of the diagrams on the upper right are an attempt to manifest this graphically. So sun is at the center of both of these diagrams. In the left-hand diagram, you can see the Earth tilted and rotating its way around the sun. But that entire green wavy umbrella, that is what's called the Parker spiral. And this is the spiral arms on which the mass ejections from the sun travel as they move out from the sun. They don't go straight out. They travel along these helical arms called the Parker spiral. And there are positive and negative electrical currents that move along these arms. And so if the arm connecting the sun and the Earth, we will feel those effects. If an event occurs that pushes an event out away from the Earth along one of the arms, we will not feel its effects. So these spiraling magnetic sheets are what carry the sun's effects to Earth. So we don't know when the sun will have these events, but as soon as they happen, we are aware because we can see the X-ray emissions, we can sense something has been thrown out from the sun, and our forecasting work can begin, again, taking somewhere between hours to 3 days for its effects to reach Earth. And it gives us a little time to react. So that's the current challenge in space weather, is to get better observations of the sun so that we can sense when those events have occurred and then get right onto the forecasting aspect to give us a sense for whether we'll be impacted or not and to what degree. So very different sets of problems than terrestrial weather. Just know that everything that goes on in space is plasma, it's not condensed matter, and it's governed by very large scale, weak magnetic and electric fields, entirely different from the way that we experience weather on Earth. But it can have very substantial impacts on us in our communications and our power systems. Yeah, that's what I have for space weather. I believe it's about time to hand to Miss Erica for some insights on the insurance side.
Thank you, Mark. My name is Erica Gage, and I am a product development analyst for the Commercial Property Product Development Department at ISO. So as we've heard a little bit, space weather has the potential to affect our power grids and our satellites. So what could happen if there's a serious space weather event today? Let's start with the first area of possibility, an event that could disrupt the power grid. So most of us have not had to deal with a power outage for more than a couple hours, or at most a day. But what happens when there is no electricity for several days, or even weeks, or even months? Most of us are worried how we are going to power our phones, computers, and tablets during short power outages. However, there are many things we forget run on electricity and how it affects our commercial property. So as I mentioned, when we think of losing electricity, our mind immediately jumps to phones, electronics, and of course, fridge, freezer, our food. What are we going to do? But now think about that from a commercial level. Our restaurants, grocery stores would experience large spoilage losses and struggle to continue business if the power doesn't come back on for days. And food doesn't just require refrigeration. Many medicines, vaccines, and even some equipment require temperature control as well. And of course, speaking of medicine, medical equipment like ventilators and dialysis machines require a constant flow of electricity too. Now, granted, our hospitals, emergency operations, or utility services have generators to back them up, but most generators run on diesel fuel or gasoline. And if the power is out for long periods of time, or is very widespread, affecting gas stations for miles or maybe even entire states, it becomes a major issue. Gas stations can't pump gas without electricity, which soon leads to fuel shortages and no way to keep those generators running. And even some businesses have to utilize water wells, which run on electric pumps. So if the power is out, the water is out, which of course leads me back to our utility services that help our commercial businesses function. Our water treatment plants also need electricity to pump water through the treatment process. And don't forget the related utility we all depend on as well, sewage collection. So we need that electricity to treat that sewage water and get it where it needs to go. Of course, all sources of communication would be affected as well if we lost electricity for long periods of time. And while cell phones may not go out immediately from a power outage, the circuits would most likely be overloaded with panic callers, and then the service gets more spotty. Then as the length of time the power is out goes up, the central switching facility finally runs out of power backup and our cell phones could potentially go dead. Businesses with landline phones might potentially work. And of course, if anybody still has a battery radio, that would be helpful. Widespread power outages could also mean traffic lights going out, bringing risk to motor vehicle crashes. Communications for police and fire departments could be compromised. Railway signals and dispatch centers could potentially be affected. So our trains with much needed product for our businesses are delayed or potentially even stopped. And then even for our urban located businesses, including, high-rise apartment buildings, high-rise office buildings, they don't usually have windows that open to the outside, and therefore they require that electricity a lot to pump filtered air through the ducts. So losing power could do more than just create an already stuffy environment. Then there are the items that happen indirectly to a business due to a space weather event. There could be looting from retail stores being vacant, or the security systems didn't shut down properly. Even if the power outage doesn't last long, even restarting equipment after an outage could be risky, particularly given that that equipment was likely shut down incorrectly when the business first lost power. And then there's the possibility of data loss if computers or storage systems are shut down unexpectedly. And then, of course, there's also the inability to receive income because businesses can't operate, or if they are able, I hope the majority of their customers can pay in cash because credit card machines aren't going to be turned on for a while. And I'm sure you can imagine the ATMs aren't working either. Next slide. And then let's switch it to, if it's not directly to our power grids, if it does affect our satellites, loss of satellites obviously can also create a communication system failure as well. And then that creates GPS outages. And that kind of GPS failure wouldn't just affect cars on the road, it would require pilots, ship captains, train engineers to rely on physical maps and analog systems to know where they were instead of their GPS, if their travels hadn't already been suspended. Satellites, and again, specifically GPS, play a role in precise time, as Cordula mentioned, and our world is held together by time, from timestamps on financial transactions to the processes that hold the internet together, to weather forecasting, not just space forecasting, but weather forecasting here on Earth. So we can see, storms, hurricanes in real time, wildfires. Without accurate time, most of everything controlled by computers is at risk. And as you heard too, more and more satellites are helping our farmers track rainfall amounts, soil moisture, crop health, and more. So if a loss in satellite information actually could potentially affect our food supplies. And while not directly impacted, power cuts would have to be made as transmission networks and power grids struggle to balance the demand and input. Our power grids actually have to be constantly monitored on the amount of input that's being delivered to them, to the demand that is required. And satellites provide a very unique vantage point from which to observe those power grids in real time, especially if those power grids are in very stranded locations. We're able to still monitor them in real time, and allowing operators to detect and diagnose those problems from a, obviously from a distance. Satellites also can be used to monitor the power grid for cyber threats. By analyzing data from the grid, the operators can detect anomalies that may indicate a malicious attack. And if satellites were down, it may leave areas exposed to a cyber attack. And then again, if GPS signals are distorted, then ground transportation is difficult and deliveries are delayed, which then of course breeds supply chain issues. And a supply chain crisis could be a long tail issue too, as we've already seen, in previous years. It could take days, weeks, months to restart. Next slide. And now I spoke very highly, very heavily, like Chicken Little, the sky is falling, but as you've heard, I'm just going to go over the fact that we've actually had examples of this impacting Earth before. The litany of potential disruptions that space weather has already caused include interference with radio communications. Earlier this month, actually, a solar flare knocked out radio communications in parts of the US and Pacific Ocean for 30 minutes. Loss of satellites or interference with satellite operation has already happened, which extends to the global positioning satellites. In February of 2022, 40 satellites dropped back to Earth only a day after they were launched due to a geomagnetic storm. We also have records of damage to our electrical grids. In 1989, as Mark mentioned, the entire province of Quebec, Canada, lost power for 12 hours thanks to a solar storm. There has been disruption to air travel as well. In 2015, Sweden was forced to shut its airspace after a solar storm disabled its air traffic control system. And then the major solar flare that erupted on August 4th, 1972, knocked out long-distance phone communication across some of our states, including Illinois. According to a NASA account, that event, in fact, caused AT&T to redesign its power system for transatlantic cables. And then the next slide. And then, of course, as we've mentioned a little bit, the granddaddy of them all, in 1859, a massive solar storm sent 2 coronal mass ejections towards Earth. It's been called the Carrington event, actually after the individual who spotted these sunspots. Massive event, 500-year solar storm. It was so bright that people reportedly woke up in the middle of the night and started making breakfast because they thought it was morning. Now, the world of 1859 is quite different than the world of 2023, but as we've been hearing, we remain vulnerable to these types of events. So what would happen if a Carrington-sized solar storm hit Earth today? Well, the good news is that we don't have to worry about sparks flying out of our telegraph machines, which is something that people reported in 1859. But the bad news is, as we mentioned, that a wide range of electronic devices, satellites, the internet, even the electrical grid could suffer catastrophic damage. And I know what you're thinking, that happened a long time ago, but the potential of a massive wide power outage or satellite failure due to a space weather event, such as the Carrington event, is not as theoretical as you may think. As you know, as we mentioned, we are heading into a solar maximum, and also in 2012, a storm that might have been as powerful or even more powerful than the Carrington event rocketed through Earth's orbit. Earth was not there at the time, thankfully, but it underscores the risk. In fact, a scientist who studied that event said that we would still, quote, be picking up the pieces 2 years after the solar storm had actually hit Earth. So all those points that I made about what could happen if electricity was out for long periods of time, that could potentially happen if we were out, if we were still picking up pieces 2 years after. Verisk's actually emerging issues team published research conducted by students from the Illinois State University Innovation Consulting Community on the possible costs of a Carrington-sized flare. And you can see their estimates of losses on the screen here. But as you can see, the cost could easily be tallied in the hundreds of billions. So, like I said, from this slide and the previous one, regardless if the space weather event is small or large, the impacts to our satellites and our power grids can be substantial, and therefore creating potentially significant damage to our business property and the time it takes to restore to normal business operations. And I will turn it back over to Mark and Cordula.
All right, so what if? Well, I feel like Erica just covered a lot of potential hotspots, so to speak, some of which we can be vigilant about, and also really just understand that these are natural events rather than adversarial, which I think is a really important distinction also in terms of our reaction. But other things may happen too that we may not have considered. And one of my favorite, you can go to the next slide, one of my favorite pet subjects is, well, we've talked about magnetic fields a lot already. And we also already mentioned that the sun's magnetic field flips fairly routinely every 11 years. And it's very chaotic, it's very fiery, it's very energized. And I already mentioned that the Earth has a much more like predictable dipole magnetic field. We've got our familiar north and south pole, and we don't need to worry about things so much because we've also got this magnetosphere, and it only comes to, we only lose that protective shield at the pole. However, the Earth actually, our own magnetic field actually also flips too, much less regularly than the sun's. But we are sort of in a geological timescale due for another flip. And the thing here to note is that the Earth's own true North Pole is actually currently shifting. It's moving from Canada towards Siberia. And as a consequence, the geographical area on the surface of the Earth where we have this increased space weather radiation reaching the surface of the Earth is also shifting. So we do want to be very mindful of this, especially in terms of how people may need to protect themselves. So not only are we getting this gradual shift of the pole and the corresponding gradual shift of the area of the protective shield at the surface of the Earth, but we are also potentially overdue for an entire magnetic reversal. So that might mean, you know, the North Pole comes out of the current equatorial region or ends up being in the South Pole. And what we can do at AER and what we would like to do is simulate this potential magnetic reversal on the Earth, and what this means in terms of space radiation reaching the Earth. And we want to be able to simulate this and can simulate it using models that can really just predict how space radiation may follow a reversal and how it might impact people and infrastructure. And I think this could really be a very profound thing if it were to happen. And hopefully we're thinking about this so far in advance that we may come up with ingenious solutions. But why would we want to do it? Well, we need to do that because how space radiation impacts people is really only so far experienced in outer space and at current polar latitudes. So we want to be mindful, we want to be scientists, we want to be vigilant about it, and we want to know what may happen. So I'm just going to leave it at that. Yeah, that's what I pretty much have to say for now. Mark, do you have anything to add there?
Just to say that as our north and south magnetic poles begin to drift, as Cordula mentioned, they are also weakening. And there is a long history in the geologic record of Earth's magnetic field flipping. It's recorded in the iron in the rocks. And we probably are just about on schedule somewhere in the next hundreds of years for that kind of flip. That flip itself basically takes that purple magnetic bottle that we visualized earlier around the Earth, that organized, symmetric magnetic bottle that protects us, and does away with it for several years. There is no magnetic field during the reversal. And that exposes us to the harshness of space. You know, as ozone protects us from UV rays and it provides a protective layer, our magnetosphere protects us in very substantial ways from space weather. And so it is a real concern, and there is a need to model and study what Earth looks like with virtually no magnetic bottle or magnetosphere to protect us. So the other thing I'll point out, just briefly, there is a really interesting physical correspondence between the sun and its magnetic field and reversals, and the Earth and its magnetic field and reversals. They're both, the magnetic fields in both cases are the product of a rotating liquid layer on both spheres. They're as different as they could be. The sun is heated, super hot plasma that convects and turns over. The Earth's liquid layer is nickel and iron in the outer core of the Earth's dynamo, but they're both rotating liquids which produce a magnetic field. And they act very differently because the sun's reversals every 11 years, ours is every hundreds of thousands of years. But there's a curious physical parallel between the two. As different as they might appear to be, there's actually a physical link in that they're both rotating liquids that are magnetic and produce a field. Sorry, I branched off into physics there for a minute, but yeah, but there are real risks associated with this that I think are not well characterized yet for us. So yeah, that's all I have.
All right, well, before we move forward, I want to thank Cordula, Mark, and Erica. That was really super interesting. Some of it, I admit, went way over my head, but sobering information for sure, and super interesting. And I also want to actually call out and thank our audience, because we are getting just inundated with questions. This is what we love, and we like trying to doing our best to answer them and seeing that engagement. do want to point out, because at the beginning I said that we're going to have slides available through PDF in a circular, but also, and I think this is kind of a first for us, we are going to plan to put up a recording of today's presentation, and we hope we can continue to put up the recordings, because that's something we get asked all the time, and that's great, and we're glad that we're able to actually do it. So the recording will be on verisk.com, I'm sorry, said it wrong, core.verisk.com/EI, EI meaning emerging issues. And speaking of core.verisk.com, you see it right here on the screen ahead of you. I've spoken about this before if you've been on our other webinars, but you know I love talking about it. I really encourage everyone, just check it out. You don't need a login. It's frictionless access. The timely information on the emerging issues that we cover. We have 69 topics that we cover, all contextualized for the P&C industry. And please also, after you check it out, come back often, because this is not a static website. We are adding new content every day. We're adding features. We've got a news feed. Do check us out. While you're there, subscribe to our weekly newsletter. I had mentioned that we are recording the webinar. The newsletter is going to tell you when that webinar has been posted. So and there'll be weekly insights coming to you, plenty of information. So with that, I am going to jump ahead to the questions that we have here that we're getting from our audience, and there are a lot. So I'm going to say right up front that if we don't get to yours, we'll get to it later, but I want to thank everyone. I guess since she spoke recently, maybe this is a fairly easy one, but Erica, isn't supply chain disruption applicable to all these scenarios? And there's a mention of inflation as well. Do you want to jump in on that, Erica?
Sure. Well, I can't predict inflation, but but yes, I think a supply chain issue of some sort would apply to a lot of these scenarios. So, I mean, if businesses can't function, then they can't make their products, and their products can't get to their customers. So, yeah, I think the majority of these scenarios it could apply.
Thank you. Fair enough. Hey, if you can figure out how to predict inflation, just could you give me a call first? I've got a few bonds to buy.
Right.
That'd be helpful.
All right.
Okay, I'll give you a break, Erica. Thank you. I'm going to throw this one to Cordula and/or Mark. How stable or predictable is the 11-year cycle, and is that cycle changing over time?
I'll take a first stab at it. I would say it's pretty predictable. It's periodic, like every 11 years. That's, yeah, it's been pretty stable. So yeah, that is something that we just count on and know that it's got an average duration of about 11 years, and that we have the solar maximum and the solar minimum in between that. And yes, if the question was how predictable it is, it's pretty good. It's the least of the headaches.
And I would say that just like you can have a cold winter one year and a warm winter the next year, this is where an analogy applies here. The activity on the sun during solar max, or the lack of activity on solar min, does vary, sort of in the 20 to 50% range. So there can be more active solar maxes and more quiet solar mins than the average. But the 11-year cycle part of it is quite predictable. Just exactly how quiet it goes during solar min, just exactly how active it gets during solar max varies year to year, and there doesn't seem to be any secular trend we can identify.
Great, thank you. Hey, Mark, don't run away from the mic and Cordula, because I do have one more, at least one more. Who monitors the observations of the sun in order to do the forecasting? Is it NASA or some other organization?
Oh, that's a really good question. Actually, more people than we may expect. So NOAA are a big agency that actually do all the solar forecasting. They're a principal agency. NASA definitely is involved too, and more recently they've become more actively involved again. We also have the Haystack Observatory and Lincoln Labs and WeDo and the Air Force Research Laboratories at Kirtland. There's some amazing solar scientists in aerospace organizations. So while it's a fairly tight-knit community, there are more space weather scientists than we might anticipate that are distributed within the civilian branches of government or the DoD branches of government. So NOAA is the big one. It's probably the most well known, but AFRL also very active, aerospace, NASA to an extent as well.
Great, thank you, Cordell. That sounds like a lot of people have their eye to the sky and paying attention to this.
Yeah.
Considering the events that could occur, it's certainly worthy of our attention. I think this next question might be more to Mark, though. Does the shifting of the true north, I think that meant, where north is, the North Pole, affect GPS navigation? Will our GPS give us wrong directions?
It's a fair question, but GPS, in fact, works on geometric factors unrelated to Earth's magnetic field. It's just basic triangulation, and the Earth's magnetic field can be in any random state, and it does not impact those triangulations that are done so accurately by GPS that we all rely on. So no connection there, thank goodness. But if the magnetic field is greatly weakened, those GPS satellites, those transmitters that we depend on for triangulation may not live very long, and we might lose the ability to triangulate by GPS.
Thank you, Mark. Okay, I'm just gonna take a look here to see if there's any others I could queue up. Well, okay, so I think we're going to wrap things up because some of the other questions, they're good ones, but some of our experts I think they're going to need a little more time to think about them and form an answer. So we know who asked the questions. We will be able to follow up with everyone. Fear not, you will hear back from us. With that, I just want to thank our speakers, Cordell Robinson, Mark Leidner, and Erica Gage. Great information today. Thank you for sharing some of your time with us, and keep an eye out for upcoming circulars. Going forward, we have more content-rich webinars coming in store, so do keep an eye out for our announcements of these future events. Keep an eye out for the recording of this event, and until then, we thank you for your time and participation. Have a great rest of your day, everyone. Bye-bye.